Euclid's Elements, Book 1, Prop 36. Parallelograms which are on equal bases and in the same parallels are also equal to each other. So let's have some parallelograms. Let's have parallelogram A, B, C, D. And let's have another parallelogram. Let's see. Let these be on equal bases and in the same parallels. So let's have parallelogram A, B, C, D, and E, F, G, H. So AH is parallel to BG, and these parallelograms each have equal bases. So that's our given, is that they're in the same parallels and on equal bases. So BC is equal to FG. What we want to prove is that the parallelogram ABCD, is equal to parallelogram EFGH. So parallelogram ABCD is equal to parallelogram EFGH. So the first thing we're going to do is we're going to connect BE and CH. Now, what we should be able to see is that we've got a blue parallelogram and a black parallelogram that we want to prove are equal. And we're going to connect them by what we're going to show is a red parallelogram. And this red parallelogram is going to be the common term that relates these other two parallelograms. So we don't know it's a parallelogram, but that's what we want to establish. So the first thing we're going to look at is we know that in this parallelogram, we know that opposite sides are equal. So we know that EH is equal to FG. And we know as a given that BC is equal to FG. Therefore, BC is equal to EH. This is through common notion 1. And we also know as a given that this whole line is parallel to this whole line. So in particular, EH is parallel to BC. So BC and EH are both equal to each other, and they're both parallel to each other. So we know from Prop 33 that if we have parallel lines that are also equal, if we join the extremities of those, so if we take the extremities from this line and we join the extremities of this line, those lines that join them, these red lines, will be equal and parallel. So these two lines that we're going to use, these lines are both equal and parallel according to Prop 33. So they're going to be equal to each other and they're going to be parallel to each other. And from that we can conclude that this figure BCHE is a parallelogram because it satisfies the conditions of Prop 34, which is in parallelogramic areas, they have equal sides and angles that are equal. And so here we have a figure formed by two sets of parallel sides that are equal, and that therefore it is a parallelogram. So if this is a parallelogram, so now we have a parallelogram in red to connect the parallelogram in blue with the parallelogram in black. And now we use Prop 35. Prop 35 says that if two parallelograms, here's a parallelogram and here's a parallelogram, if they're on the same base and in the same parallels, then they're equal. And so you can see the black one and the red parallelogram are each on this base and they're each in the same parallels. Therefore, those parallelograms are equal. So we're going to say parallelogram EB, what are we calling this? Oh, we're calling it something else. We're calling it BC HE is therefore equal to our black parallelogram EFGH. Likewise, now let's look over here. the blue parallelogram and the red parallelogram are on the same base and in the same parallels. Therefore, the red parallelogram, BCHE, is likewise equal to the blue parallelogram, ABCD, again through Prop 35. Well, now it's obvious these two parallelograms are equal to this parallelogram. Two things equal to the same thing equal to one another. Therefore, the black parallelogram, EFGH, is equal to the blue parallelogram, ABCD. Common notion 1 again. Therefore, we have shown that if you have parallelograms on equal bases contained by the same parallels, then those parallelograms will be equal to each other. The blue parallelogram is equal to the black parallelogram. And that's what we were supposed to prove, so we conclude our proof, QED.